Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. That's my Bene Gesserit voice. Testing on YouTube. All right. Works on YouTube. Now we just got to wait for X, and then we're good to go. How's it going? 2ARX, Isaac Perez. Should be live here on X in a minute, and then we will get started. All right, I think we're almost there. Hope everyone is having a nice Sunday, whatever time it may be in your respective places. I know we have quite an international audience, so whether it's morning or afternoon or nighttime for you, welcome. All right, I think we're live on X. Let's confirm that it's working. Broadcast is not available. Let me try again. Testing. Okay, it seems to be working on X as well. All right, let's go ahead and get started then. Let me spit out this gum. How's it going, Ed, Work, Ilya, Timothy? What Hupo means. Hupo is the two first letters of my full name. So my name is Hugo Ponti. So it's Hupo. No. I don't have a fake name. You know, I don't have some fake identity. Unfortunately, you can literally figure out exactly who I am. But I got nothing to hide. All right, let's blow this horn and get started. All right, welcome everybody to another Hupo stream. This is going to be a good one today. So the name of the stream is called Multi-Modal Pre-Training, but it's not necessarily the best title. I made this thumbnail before I even necessarily read the paper. We're going to be talking about Apple's new MM1 model. So Apple, which is one of the big tech companies known for their iPhone and their MacBooks, usually their hardware, they've been around for a long time, but they haven't really participated in the AI explosion recently. They've kind of been slow to do much of anything at all. But then out of nowhere, on the 14th of March, 2024, this week, they basically drop this paper on Archive, and this paper is really good. It is extremely extensive. Look at that. It's over 40 pages of a huge amount of detail. So they go through all the different ablations, all the different experiments. They talk pretty much everything that you could want, all the learning rates, all the different things, all of the data sets that they used. It's very comprehensive. And for a company like Apple, that is very unusual, right? Apple for a very long time has been known as one of the more secretive companies. I have never really worked at Apple myself, but from friends who have, it's the kind of culture where you go and you eat lunch and like you're talking to someone else who works on a different department, and they're not even allowed to tell you what they work on. So it's like this company that is known for secrecy, and then here they are dropping probably the most open AI paper, at least in the vision language model space, for a big tech company. Meta, or Facebook, is also known for being quite open source, so kind of a weird place that Facebook or Meta and Apple are the current true OpenAI companies, and Google and Microsoft are the kind of closed AI companies, Microsoft, of course, being OpenAI. There are some things that they don't mention in this paper, so I'll kind of drop that there as a cliffhanger Easter egg. There's two things that they don't mention in here that is a little bit suspicious that I don't like, but for the most part, this paper is quite good, and I'm quite excited to share it with you guys. How's it going, Majetti, PC, and Rachel? Okay, so let's start off by just looking at some of the stuff on the first page here. We got a huge amount of authors here. We got what they call first authors. So these are the two people that really did most of the work. And then you got your senior authors, which are going to be your people that are slightly older, slightly more prestigious. And then everyone in between here, they call these core authors. I'm not exactly sure what the distinction there is, but if you scroll all the way to the bottom, past the appendices, or actually maybe just before the appendices, where was it? Here, it's at the very end, sorry. There's a section called author contribution. So I've seen this before in some of the Google papers, but they go through what every single different person did. So if you have a huge amount of money and you want to build your own 25-person in-house ML team at your startup, maybe you can use this as a rough idea of the different types of people you should be hiring. Or you know what? Maybe you don't do that because maybe you just use the AI software engineer and you don't hire any humans. But jokes aside, let's actually start by reading this abstract. In this work, we discuss building performant multimodal large language models. So right off the bat, this is actually one of the things that I did not like about this paper. Multimodal large language models is not the correct name for this. I think if you look at the community and the other papers that have come out, I think the real word for this is called vision language models, VLMs, right? Multimodal means there's multiple modalities. Images are a modality, text is a modality, audio is a modality. If you had some kind of like vibration data, that would be a modality. But there's only two modalities here, and it's the modalities of vision and the modality of language. And all the other papers that we read use VLM because this large in large language model in LLM kind of lost its meaning because now there's big LLMs and small LLMs and everything's an LLM and the large doesn't mean anything anymore. So I really liked the VLM just because it was easier to say, it was less letters, and it was more concise. Multimodal large language model is a little bit verbose and isn't even necessarily correct. But, you know, Apple's going to be Apple, and they pulled off this one in the VR community too. So when Apple released their VR headset, instead of calling it a metaverse headset or a virtual reality or augmented reality, they decided to kind of rebrand using the word spatial computing. And people were actually releasing the marketing boilerplate that Apple released with that, and they were very insistent that people use the words spatial computing to describe their VR headset. So maybe there's kind of a similar thing happening here where Apple wants to kind of own the category. They want to own the SEO, the search engine optimization. And rather than saying, okay, we're going to release a VLM because everybody else has VLMs, they're going to say, okay, we're going to release a multimodal large language model, an MLLM, because like that, we can kind of own the name for it. So I'm not a huge fan of that, but whatever. We'll let that slip because most of this paper is quite good. Okay, in particular, we study the importance of various architecture components and data choices through careful and comprehensive ablations of the image encoder, the vision language connector, and various pre-training data choices. We identified several crucial design lessons. So this is going to be kind of like the Stable Diffusion paper we read a couple weeks ago, where they show you all the different choices that they had to make and the ablations that they did to compare those different choices. And ultimately, you come out of this paper with different lessons that you've learned by not performing these experiments yourself, but having Apple perform them for you. We demonstrate that for large-scale multimodal pre-training, using a careful mix of image caption, interleaved image text, and text-only data is crucial for achieving state-of-the-art few-shot results across multiple benchmarks. They do claim state-of-the-arts here, but it's only compared to other published pre-training results. So this is technically not state-of-the-art on everything, right? GPT-4 vision still seems to be state of the art, but the way that they kind of get around this is by saying that they achieve competitive performance on established benchmarks, but then they achieve state-of-the-art results across some benchmarks. So they're state-of-the-art on a couple different benchmarks compared to some models that are kind of picked because they're a little bit worse, but they're competitive on kind of the more generic benchmarks. We show that image encoder together with image resolution and the image token count has substantial impact. The vision language connector design is of comparatively negligible performance, and this is kind of a big one here for the Rich Sutton bitter lesson fans, because a lot of these VLM papers that we read on previous streams, they focused a lot on this vision language connector design, and it turns out that it's not that important, which is great, right? Because it means that we don't need to worry too much about the engineering of the specific connector. Sometimes they're also called the projector. But the bad side of that is that it means that there's no real room for individual engineers and researchers to come up with novel things. If everything is just determined by the image resolution and the scale of the pre-training, then really it's just an arms race to see who has the biggest amount of money to spend on the pre-training rather than some kind of competition around the best idea. Okay, by scaling up the presented recipe, we build MM1, Multi-Modal 1, I guess. So eventually they're going to release MM2, MM3, and so on. A family of multimodal models up to 30 billion parameters consisting of both dense models and mixture of expert variants that are state-of-the-art in pre-training metrics and achieve competitive performance after supervised fine-tuning on a range of established multimodal benchmarks. So you're going to see kind of the standard curriculum here that is emerging, where you have a pre-training stage and then you have this fine-tuning stage. Thanks to large-scale pre-training, MM1 enjoys appealing properties such as enhanced in-context learning, multi-image reasoning, and enabling few-shot chain-of-thought prompting. Okay, so we're going to start off by going all the way to the bottom, actually, and looking at a couple of the results that they put here, because I think it's worth kind of looking at these in context and getting an idea of what this model can do before we jump into the nitty-gritty. So here we have in the appendix section D qualitative examples. For example, we have count the number of apples in the image, and it's counting the number of apples in the image. We have what are all the scene text in the image, and here you have a picture of a bridge with some graffiti written on it, and it successfully gets that. So this is quite impressive, right? It's OCR, or optical character recognition. It can basically get the words perfectly. The impressive thing here is that not only is this handwritten, and not only is it relatively kind of fuzzy and hard to see, but it's also very small. So the relative size of the text compared to the full size of the image is quite small, so that's impressive. This is also OCR here, so it gets all of these numbers. And the reason this is impressive is because the numbers are kind of shifted and they move, and also the numbers are bigger. So sometimes if the text is very small, it's hard to do OCR, but also sometimes if the text is too big, it's hard to do OCR. So they're kind of showing their range here on the OCR. And then I also thought this one was worth looking at. So here they show some examples of basically the language model being able to say no, which is something that a very common type of hallucination is that the LLM is heavily encouraged, usually because of the instruction tuning or preference optimization, to basically never say no to the user, always assume the user's right. So here they have an example of exactly the opposite of that. Can you find the red ball near the gray cat? There is obviously no red ball, and here we have the model telling you that. No, there is no red ball near the gray cat. The cat is sitting on a pillow. Can you see the bright blue feathers on the bird's wings? No, the image in the bird in the image does not have bright blue feathers. So this ability to say no is, I think, quite impressive, and it means that it's been tuned correctly, right? So that's what you really want. You want a model that can tell you when you're incorrect, not a model that's just going to go with whatever you say because it's too afraid to tell you that you're incorrect. So pretty cool stuff. They also have some examples here showing how you can interleave. So you can interleave text and images. So here you see here's the operating menus for this coffee machine, and there's a couple different images interleaved with text. So you have text, image, text, image, text, image, text, image, and then it's able to answer a question related to that. So you can interleave the text and images. It seems to be pretty good in terms of giving you factual information and not just hallucinating something that agrees with you. And it can do all the kind of standard things such as OCR and counting. So qualitatively, this does seem pretty good. And let's go ahead and get started. So let's go back to the beginning of the paper here into the introduction section. Let's minimize this a little bit. Okay. How's it going? No Free Will, Ed, 87GN, and Cheyenne. Okay. Do they mention where their data set is from? That's a question from 2ARX. They do. So there's a specific figure here. Right here. Right here. Right here. Right here. This one? I think this is the multimodal. No, these are evaluations. Okay, I think it might be down here. Yeah, here we go. So this is the list of data sets used for supervised fine-tuning, and then they also list the data sets that they use for the pre-training somewhere else. I'm not going to be able to just pull it up, but they do list all the data sets that they use. There is one internal data set, so they do mention that they have an internal data set, but for example here, damn, I should have had these pulled up. They do mention that there's one secret internal data set, but overwhelmingly, the majority of the data that they use, they mention, and it's all like publicly available data. Okay. Multimodal large language models are large-scale foundation models that consume image and text data and produce text, right? So image and text, two different modalities, hence the multimodal. And the large refers to that when large language models first came out, they were quite big compared to other models, hence why they were called large language models. But large doesn't really mean anything now because all the models are big. Two categories, closed models and open models. So your closed models are going to be things like GPT-4 Vision, whatever Claude is using, right? A bunch of these services that provide vision language models as well. Most of them are closed. You really have no idea what they trained on, how they trained it, what the model architecture is, any of that. Here, they're going to say this is an open model. And they do talk a little bit about the word open isn't entirely clear anymore, right? So back in the day, open source meant that you just release the code. And back when intelligence was the result of a bunch of human-written code, if you release the code, that's really all you needed to know, right? So the code was everything that you needed to know what was behind some kind of intelligent behavior that your computer was doing. But with deep learning, there's a lot of different pieces, and people only release parts of the pieces. So for example, model parameters might be released with the training configurations and the description of the data, but there might be no release about the process they have undergone to arrive at their algorithmic design choices, especially regarding multimodal pre-training, which is the case even in some of the Meta and Google papers, which are supposedly open, where they kind of share some details. They only share some of the details. So we're seeing a little bit of a battle, I guess, over the definition of the word open, especially when it comes to deep learning-based models where you have the curriculum, you have the data, you have the model architecture, you have all the ablations, all the experiments that you performed. There's so many different details there, and nobody's really giving you all the details. And Apple does give you close to all the details. There is some details that they do not give you. I'll keep teasing that. But compared to the other big tech companies, this is quite good in terms of what they tell you. Ultimately, they perform a bunch of experiments, and in the following order of importance, these are the most important things for the final performance of the model. Image resolution, so big images means better performance. That kind of makes a ton of sense. The visual encoder loss and capacity. Capacity is just a way of saying how big that visual encoder is. So big visual encoder is going to be important for performance. The loss, we're going to go into that once they go into that. And then the visual encoder pre-training data, which is basically just saying what data you're training that visual encoder on and the mix of that data. The mix is basically like what percentage of it is text only, what percent of it is these kind of like interleaved image and text, what percent of it is just captioned images, and so on. So there's a couple different types of data. Few shot and text only performance, interleaved and text only training data is of paramount importance, while for zero shot performance, caption data matters the most. Trends hold after supervised fine tuning. They scale up their models, so they're going to have models at different sizes. You're going to have a 30 billion parameter model, which is going to be the most performant model, and then you're going to have the 3 billion parameter model, which is going to be the smallest one. You want to have different sizes because, obviously, being Apple, they're going to want a model that fits on an iPhone, right? They want a model that they're going to be able to perform inference on the edge. Inference on the edge just means you're using your iPhone to run the model, versus they're going to want a model that is the best possible performance, that's probably going to run in some GPU, in some data cluster, buried away in some random country with a very low energy cost. So that's going to be the 30 billion parameter model, and then the 3 billion one is going to be the one that runs on your cell phone. They do have a MOE with 64 experts. This is kind of weird. Usually the mixture of experts, which is a specific type of architecture, you don't see this many experts. Like usually it's 8 experts, but here they kind of really push the limit here. They have a 64 expert MOE, and then they have a 32 expert MOE. These models outperform most of the relevant works to the best of our knowledge, achieving state-of-the-art compared to EMU2, Flamingo, and Idifix, which are not necessarily super strong models, but achieving competitive performance across 12 established benchmarks. So they're state-of-the-art compared to some kind of more open, not that great models. Flamingo is a little bit older. EMU2, I think, was last year as well. So not quite state-of-the-art, but competitive. All right, related work. Do they show some failure cases? They do not show any failure cases. Related works. Build upon a strong pre-trained autoregressive LLM. We aim to provide details regarding all of our components of our pre-training strategy, from hyperparameters to data to architecture. Okay. Recipe for building. There are three major axes of design decisions. So these are kind of the three main design choices that you have to make. So the architecture, we investigate different pre-trained image encoders and varying ways of connecting the LLMs with these encoders. We consider different types of data and relative mixture weights. The mixture weights is basically the data mix. So how much of this, how much flour is there, how much sugar is there, how many eggs are there, right? The mix of the data that actually goes into the pre-training and the fine-tuning, right? Because it's a 2-stage training pipeline. And the training procedure, what parts of the model to train at what stage. Here they're referring to, if you look at some of the previous VLM papers that we've looked at, usually what people do is they use a pre-trained image encoder, and then they'll keep that frozen, and they'll push gradients into these little connectors, or sometimes called projectors. But here they're not going to do that because they're Apple, so they have a lot more money, so they can train a lot of these things from scratch. So they tried all of that, right? They'd say, okay, keep it frozen, not keep it frozen, train it from scratch, don't train it from scratch. So they kind of did all of these different experiments and are summarizing these results for you. Training a large MLLM can take substantial resources, right? So what they're going to be doing is that they're going to use a smaller base configuration that we ablate from. And this is not new. We've seen this pretty much everywhere, that performing these sweeps or these experiments where you're trying all the different design choices, you can't do that on the biggest models, right? Training a 30 billion VLM from scratch and doing 100 different experiments of that is, even if you're Apple, that's still way too much money. So a lot of these ablations are done with the small 3 billion parameter model, and then they just assume that whatever the results they get from that also apply to the 30 billion parameter model, which we still don't even know if that's necessarily true, right? Like the entire community is kind of acting like that's completely fine to do, and there's some papers that kind of provide some theoretical reassurances that it's okay to kind of sweep in the hyperparameter space using small models and then just simply assume that that's going to work for the big models. But we're not 100% sure that that's the case, right? So it would be interesting to maybe 5 years from now look back and say, hey, actually, this design choice that we came up with from studying this 3 billion parameter model, and we just used it for the 30 billion parameter model, it actually ended up not being a good design choice. And if only we would have done this hyperparameter sweep with the 30 billion parameter model, we would have realized that this was the best thing to do. But, you know, we're all kind of limited by our GPU budgets right now, even Apple. So for now, we have to use this pattern of sweeping in the small models and then just taking those learnings to the big models. Okay. The image encoder is going to be a VIT large 14. This is a transformer, a vision transformer. The L refers to the size. There's different sizes of these VITs. There's VIT small, VIT base, VIT large. And it's trained with a clip loss, which is a type of contrastive loss, on DFN 5B and VCAP 300M, with an image size of 336 by 336. So this is the image encoder right here. So this is your VIT large. The VIT large is what's consuming this image here. And then that has to, at some point, be fed into this language model here. So in order to take what's coming out of this image encoder and make it fit or like compatible with what's the LLM here wants, the LLM wants tokens, right? The LLM is consuming these text tokens, and then you want whatever comes out of this image encoder to kind of look like text tokens, at least be the right size, you know, and kind of similar enough to these text tokens that you could just feed it in as if it was more text tokens. But what's coming out of this image encoder is not going to be that. So you have what's called these connectors. They're sometimes also called projectors. So here, for example, in this paper, they call it a projector. So here, this is a paper where they kind of do this ablation study on a bunch of different types of projectors or connectors, but it's going to turn out that it doesn't matter. So the conclusion that Apple comes to is that the architecture and design choice of this projector is actually not that important at all. That what matters more is the capacity of this vision encoder and the image resolution, but the projector or the connector is effectively what changes these visual features here into these visual tokens here. Okay. Pre-training data, a mix of captioned images, 45% captioned images, 45% image text documents, and 10% text-only data. And finally, the language model that they're going to use is going to just be this tiny little decoder-only language model of 1.2 billion parameters up here, right? And it's a decoder-only model in that it basically only autoregressively predicts the next tokens, which are going to be text. So the output of this model is just text token, text token, text token, text token, text token, until it finally outputs a end of sequence text token. And here are all the different evaluations. So they're going to evaluate this on COCO captions, no caps, text caps, VQA, text VQA, VizWiz GQA, and OK VQA. VQA means vision question answering. So you can see that all of these are basically vision question answering benchmarks. And then COCO captioning is basically an image, and then you have to get the caption right. 32 and 64. Can they pre-train on Apple Silicon, or do they still need NVIDIA GPU clusters? This is a question from Work. And Work, you actually are the lucky winner because you figured it out. So when I started reading this paper, I mentioned there's one thing that they don't talk about here that is very important, and that is the hardware. So I read this paper, and I was like, they don't mention the GPUs at all. And I was like, okay, let me search for GPU. Nothing. Let me search for TPU. Nothing. Let me search for chip. Nothing. Let me search for silicon. Nothing. So they somehow don't mention at all what they trained on, which seems like a very important thing, right? We don't know if they trained this on NVIDIA GPUs. We don't know if they trained this on Apple chips, which would have been pretty awesome if they did, but I think the reason they don't mention it is because it's an NVIDIA GPU. I think if I had to guess, this is either trained on NVIDIA GPUs or on TPUs, and the reason I mentioned TPUs is we'll show that in a second, but they don't mention the hardware that they train on. So it's literally a 42-page paper, and they don't mention what they train this on, which is a little suspicious, right? And I don't like that. I wish they would have just told us and been honest, but I think they just didn't want to let you know because they probably at some point, like, I don't know what's happening inside Apple, but they have to be considering making some kind of GPU-like chip with their M1, M2, M3 chips. So something that is very good at parallel computation that you can use for distributed training of these very, very large foundation models. There's no way they're not working on that, but it's going to take forever for them to actually implement and then put that out there, right? Hardware development cycles are so slow that for sure they weren't able to do that in time for this paper. So I think the reason they don't mention that they trained on likely NVIDIA GPUs on this paper is because they are hoping that by the time they release the second paper, maybe they'll have a big enough cluster of their own internal secret chip that they can mention that they train on their own internal secret hardware, right? Because that would be kind of sketchy if they talk about, hey, we trained this on NVIDIA GPUs because even though we're a hardware company and we make very, very, very good chips, we make chips that are kind of irrelevant for distributed training like this. So that's why I think they don't mention what hardware they train on. But if only they would have, this paper would have been perfect, but they do not. So any comments on the number of MOE they use? Is having good, another question from work, is having lots of MOE good? What is the right balance? So the more, whenever you're doing these mixture of expert models, you're inflating the capacity of the model, right? So the more experts you have, you can think of it like the size of the model is bigger and bigger and bigger, right? The way that mixture of experts work is that the model size is getting bigger, but you're using a smaller amount of the models. So they have a specific section that goes into this, but they only use 2 of the experts at a time. So even though there's 64 experts here, for any particular token, they're only using the output of 2 experts in order to determine the attention for the next layer and the next layer and the next layer, right? So the problem with these mixture of experts situations is that you need to, whenever you're performing inference and you have this model on the GPU, if not all of your experts can fit on the GPU, which is usually the case, you're going to have to load experts into memory and out of memory every time you're going into each layer, right? Because the mixture of experts is happening at every single layer. So usually, the reason why you see mixture of experts with 8 experts is because when you put GPUs in the cloud, usually they're in these server racks that have 8 GPUs. So 8 GPUs means you can fit experts perfectly on each of the 8 GPUs, and it all kind of works out so you never have to load things in and out of that GPU VRAM, which is quite expensive. But here they have a mixture of expert with 64 experts, which is kind of like a weird MOE, but ultimately the answer to your question work is that, yeah, you could, if you made this 128 experts, 1,000 experts, it would perform better, but at some point, the extra memory required to have all those experts would start to become enough of a burden that it wouldn't be worth it. Okay. Let's keep scrolling. So we were looking at the related work, the recipe, the training, the best model architecture ablations. So now the image encoder pre-training. How to best pre-train a visual encoder and how to bridge the visual features to the space of LLM. So how do we take these visual features right here that come out of the vision encoder and bridge them or modify them or adapt them or project them or connect them such that they can be turned into visual tokens that can simply be appended to these text tokens and then consumed by the large language model. Most VLMs or MLLMs use a clip pre-trained image encoder, while recent works also started to explore vision-only self-supervised models such as DynoV2 as the image encoder. So there's a lot of these image encoders, right? People have been training these image encoders for a very long time. There's image encoders that are convnets. There's image encoders that are transformers. There's image encoders that are trained with a clip loss. There's image encoders that are trained with more of a reconstruction loss. There's a lot of different types of image encoders, and the tricky part there is that these image encoders are slightly different, right? So the representations that are produced or the visual features that come out of these vision encoders depend on a lot of little details. So it's kind of a tricky problem to pick the right one, right? So here they kind of bucket them into 2 main categories. We're going to have vision encoders that are trained with contrastive losses, which endow a visual encoder with semantic knowledge, and automatically curated large data sets and synthetic captions have led to even stronger encoders. And encoders that are trained with reconstructive losses, where those kind of explicitly capture all parts of an image. Okay, so I have some pictures here, some figures from other things to kind of explain what this looks like. So here I have an image that's trying to show what a contrastive loss does. What a contrastive loss does is you feed pairs of images, usually more than that, but you have one image. Here's an image of a basketball player called Stephen Curry, and they feed it through a convnet. This would be the vision encoder. And then you're going to get this little vector here, which is the vision representation, right? And then you feed this picture, which is another picture of the same basketball player, right? And that's why it's a positive example, because these two represent the same semantic concept, which is this basketball player called Stephen Curry. And you feed that image into this vision encoder here, which is a convnet, and it gives you another little vector. So you know that this vector and this vector, because they both represent the same semantic concept, should be close together in this embedding space, right? So these little vectors here, they're basically vectors in extremely high dimensional space, but you know that the similarity between those vectors, or the position of those little dots, should be close together. So you pull those together. You have a loss that pushes those points together. And then you have here negative example. So here's two different basketball players. You feed both of them through the vision encoder. You get two vectors, and you know that these should be far apart. So your loss will push those apart, right? And a contrastive loss is basically a contrastively trained image encoder or vision encoder. Is you do this on a very, very large data set for a very, very large amount of examples. So you're just constantly feeding it these examples of these two things should be close together. These two things should be far apart. These two things should be close together. These two things should be far apart. These two things should be close together, right? So that's where the contrastive and the contrastive loss comes from, because you're contrasting things that are positive or should be similar and things that are different and should be far apart, right? That's a contrastive loss. Now let's look at a reconstructive loss. The reconstructive loss is this. So here you have a encoder-decoder setup. You have an image that's being encoded into some representation. In this case, this encoder here would be your vision encoder. And then it's decoded into this output here. And you can see this should be this, right? So then a loss that you can use here is called a reconstruction loss, where you're basically maybe just a mean squared error, and you're saying, okay, every single part of this image should match every single part of this image. So you're saying this pixel minus this pixel, 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 right? And that's a reconstructive loss. So a contrastive loss is going to give you semantic knowledge, versus a reconstructive loss is going to basically explicitly capture all parts of the image, right? So they're different types of losses or objective, which results in slightly different features. And I have one more image here to really drive the point home. Here is a clip, which is trained with a contrastive loss, and here you have Dino V2, which is more of a reconstruction loss, although it's slightly different. It's a little bit more complicated than that. But here you're looking at the similarity between this image and this image and this image and this image. If you're using clip features, note how the similarity is kind of the same here. So it's always an image of a pizza. So the similarity between the vectors of these is 83%, 82%, 82%, right? Because semantically, it's the same exact thing. It's just a picture of a pizza. So the clip little vector that comes out of that clip vision encoder is effectively capturing the fact that this is an image of a pizza. Therefore, two images of the pizza should be the same thing, right? But if you look at what's coming out of this Dino V2, the similarity scores here are way lower, because Dino V2 is less semantic-y, right? It's not outputting, hey, this is an image of a pizza. What it's really outputting is more nuanced, right? It's looking at more of the fine details of like, okay, this is wooden and there's a fork here. Here, this is metal and there's no fork here. Here, there's a little bit of wood and there's two pizzas, and here there's this pizza's cut, right? So like, Dino and these type of reconstructive losses result in vision features that are more nuanced and more kind of low level, right? So it's more dealing with all the fine details in the image as opposed to kind of a high level semantic concept. So that's the difference between these, right? But one of the things that they do potentially poorly in this is that Apple just uses one image encoder, right? So they say, okay, well, we're going to compare contrastive versus reconstructive loss and then just use the one that works best. But you don't actually have to do that. And to illustrate that, I have a image here, or a paper. This is a paper that we read in a previous stream. This is called MUSI, Polyvisual Expert Vision Language Model. And in this paper, they don't choose one image encoder, one vision encoder. They just use all of them. So if you see here, they feed this image into a clip image encoder, into a SAM image encoder, which is trained to do segmentation, into a OCR type image encoder, and then each of these produces little tokens, and then they basically just concatenate all of those together. So this is a solution that the open source community already figured out, where rather than having to choose one specific type of image encoder that it's either trained contrastively or it's trained using this reconstructive loss, you can use these ensembles of image encoders, right? So just use multiple different image encoders that are trained with slightly different losses and are good at slightly different things, and then you're going to get a better result. The only negative of doing this is that it's more computational overhead, right? Having a single image encoder is going to result in less inference time and less tokens, right? And ultimately, this LLM here is going to have some limited context length where it's only going to be able to consume some amount of tokens. So if you only have one image encoder, that's less tokens total than if you did what they do in this paper and you have multiple image encoders that are basically giving you slightly different features, but now you have way more tokens, right? And you can use this type of ensemble trick, not even just with the image encoders. You can also use it with text encoders. So here I have the Stable Diffusion 3 paper, which we also read on the stream, and they do the same ensemble trick with the text encoders. So here you can see they take your caption, which you're using to condition the diffusion model, and they feed it through 3 different text encoders: clip G14, clip L14, and then T5 double XL. So much like different image encoders focus on slightly different things, and an ensemble of them is better than any one of them individually, the same thing is true for these text encoders. So I thought that was maybe one thing that Apple could do a little bit better, is maybe use an ensemble of image encoders, especially now that we're moving into a world where the context length of these LLMs is getting bigger and bigger and bigger. So if you're getting a bigger and bigger context length and the GPUs are getting bigger, so you don't have to worry about inference time as much, using an ensemble of different image encoders is probably going to result in better performance than using a single image encoder. Damn, you guys are popping off. Unimodal or both text does not become single. Does the same thing happen? Okay, I think I hope I answered most of your questions. I think I answered them in that rant, but if you have more questions, let me know. Okay. Blah, blah, blah. They use these. Contrastive losses. Explicitly capture all parts of the image. Okay. So throughout this paper, they're going to basically have these little lessons. So we're going to keep scrolling through here, but they basically have these like little bolded sections here where they basically summarize their lessons. So if you don't have time to read this entire paper, one thing I would recommend doing is just scrolling through it and then read all these little lessons here. So data lesson 1, data lesson 2. It's basically just a summary of all the stuff, and they're quite concise. So one summary that they have here, at least when it comes to image encoders, is the image resolution has the highest impact, followed by model size and training data composition. Okay. Increasing image resolution from 224 to 336 increases the model size from VITL to VITH, and adding more synthetic captions yields performance improvements. So what they're talking about here with this data set of synthetic captions, this is a trick that we mentioned seemingly every single stream, but a lot of these captioned data sets, where a captioned data set is you have an image and then a little caption that goes along with it, the caption is actually quite small. It's not a lot of tokens. It's not a lot of detail. So what people do now is they will augment these captions. They will turn that little one-sentence caption into a paragraph, and having a more fleshed out paragraph, more text tokens to complement the image, usually results in better performance. So they're using specifically this VCAP 300, which is a data set that has these synthetic captions. Okay. Vision language connector, or actually here, two image resolution and 2 image token sizes. So here you have different size images, 224, 336, 336, and then they also want to look at the amount of tokens. So here's a 336 resolution image with 64 tokens and a 336 resolution image with 144 tokens. And what do they mean by that? Okay, so I have a picture to show that, and here, this is kind of like from some other unrelated paper, so don't worry too much about like the stuff down here. What I really want you to focus on is the stuff up here, right? So where you can take an image, here's an image of 2 cute little koalas, and you can patchify it or turn it into these patches, and you can determine the resolution of these patches, right? So whenever you go here and you look at, for example, this is Apple's Hugging Face. By the way, they have a pretty good Hugging Face. They have all their models here. So the specific clip VITH, which is the vision transformer, huge, this number right here, 14, that's the patch size, right? So the patch size determines basically how many of these patches you have. And the more patches you have, you're going to have more tokens. So you see here how more patches results in more tokens. Not a lot of patches results in not a lot of tokens. So the benefit of this small patch size or big patch sizes and not a lot of tokens, is that you don't have to take up a lot of the context of the transformer, right? So this transformer here, this language model, it has a limited context length. So if your image encoder outputs a huge amount of vision tokens, you're going to just chew up all of that context. So there's a little bit of a trade-off where they would like to use as little vision tokens as possible. So they try either 144 tokens or 64 tokens, and ultimately it does seem like having more tokens results in better performance, but just barely so. You know, it's just like 30, 31, 32. You get a little bit more of a difference here, 55, 57, 59. But, you know, if you're dealing with small context, maybe you use 64 tokens rather than 144 tokens. But it seems like the kind of scaling law is in effect here, and the bigger you make the image and the more tokens you use as the output of your vision encoder, the better performance you're going to get. One ablation I would have loved to see is if you had 64 tokens coming from a clip image encoder and then 64 tokens coming from a dyno image encoder. Would those 128 tokens be better than the 144 tokens that come from a more finer patch resolution clip image encoder, right? So if you're going to be using 144 tokens anyways, why not use 64 tokens from two different image encoders in an ensemble, right? I don't know. I thought that that's something they didn't really do here. They kind of just like only use one image encoder and then just say more or less tokens coming out of that rather than two different image encoders. We would like to capture as much detail from the image as possible, fulfilled by increasing the number of image token embeddings. On the other side, especially in the case of multi-image input, having a large number of input tokens per image is computationally challenging. We consider using 64 or 144 tokens. Okay, now we're going to look at the connector. So now that's the ablation on the vision encoder, which, by the way, they train from scratch. So I think they mention it maybe here. I think they might have mentioned it later, but they trained this vision encoder from scratch, which is actually kind of unusual, right? Most of the VLM papers that we read, they don't train these from scratch. So here, this Musi Polyvisual Expert, this is from Fudan NLP. These guys did not train this clip image encoder. They did not train this image encoder SAM expert here. So this is trained by Meta. This is trained by OpenAI. Right? And the reason people don't train these is because it takes a lot of compute and money to train these, so you might as well just use the ones that are publicly available. So in most of the open source community works that we see, for example, Stable Diffusion did not train this clip G14. They did not train this clip L14. They did not train this T5XXL. So they're using pre-trained encoders that other people use. And because they're using pre-trained encoders that other people use, they usually freeze them, right? So this little freeze sign means that they didn't touch this. They got this from the Facebook Hugging Face repo, and then they say, okay, we're just going to use this SAM image encoder, which was trained by Facebook, and we're going to freeze it so that we don't change any of the weights here, and that's it. But in this Apple paper, they wanted their own clip, right? So Apple doesn't want to be using OpenAI's clip. They don't want to be using Meta's Dino V2 image encoder. They want to make their own image encoder from scratch so that they can be like, this is our fucking image encoder and we trained this thing from fucking scratch. So that's this, right? So here are their clip image encoders. They have a VITL, VITH, VITB, VITH, which I guess makes sense, right? If you're Apple, you don't want to be necessarily using other people's stuff, but guess what? They were probably using NVIDIA's GPUs, so you know, how about that? Okay, now that we're done with the image encoder, let's look at this connector. Damn, what are you guys talking about? Fukushima Neocognitron? Oh, that's what the CNN used to be called? There's still competitive CNNs. I think the ConvNext, this one, ConvNext, a ConvNet for the 2020s. There's still ConvNets that work quite well. And even yesterday, we were looking at, for example, Mamba papers. And Mamba papers are different architecture as well that also works well. And I think there's too much focus on this architecture, Transformer versus Mamba versus ConvNet. what this paper actually says is that it doesn't matter, right? So like literally right here, when they're looking at this connector, contrary to what has been reported in the literature, different architecture designs do not appear to conclusively produce stronger models. All three architectures achieve very similar results, which is the correct intuition from the Rich-Sutton-Bitter lesson, right? The Rich-Sutton-Bitter lesson is that humans like to spend a lot of time thinking about the engineering of things, and the engineering, really the most tangible thing that you can change is these model architectures. But what really matters is the data set and the scale, right? The image resolution, the capacity of the vision encoder, the pre-training size and mixture, right? Those are the things that matter, and those are all the things that you can really only improve via scale. These architecture choices, they're just playing this like one-up battle where, oh, we're better than the ConvNets of last year, and then the ConvNets are better than the transformers of this year, and then the transformers are better than the ConvNets of last year, right? It's like this kind of like pointless arms race where everybody's just publishing papers to get a little bit of novelty, but ultimately, really what we should be focusing on is just the scale, because these architecture design choices don't appear to conclusively produce stronger results. The different ones that they consider here, I would refer to this paper. This is the paper that they reference here. And in this paper, they look at a couple of these different connectors. This is the simplest type, would be a linear projector, but they also basically come up with these other ones here. They call the C abstractor and the D abstractor. The C abstractor stands for a ConvNet, a convolutional abstractor, and the D abstractor is a deformable attention-based abstractor. So you can see they're a little bit complicated here. Basically, rather than just using a linear projection layer, which is what most of the vision language model papers do, the C abstractor just adds some residual blocks here, and then this average pooling. The D abstractor adds a little self-attention block. So it's kind of like a little mini transformer and then like a little mini ConvNet. But it's back to the bitter lesson. This is kind of just a waste of time, because you could just use the simplest possible one here, which is the linear projector. And that ends up working pretty much as good as the other ones. I don't know why they decided to go for the C abstractor if they said that the architectural design choices do not appear to produce stronger results. At that point, just use something super simple like average pooling, right? Average pooling is probably the simplest way to do that. This would be this. So in average pooling, you're just basically, you reduce the size of what's coming out of something by averaging. So here you can see how these four values are averaged like that. This is a way to downsample into whatever size you need to match the text tokens. Okay. All right, you guys are still arguing about ConvNets? Pre-training data ablation. Large-scale and task-appropriate data is of paramount importance. They're going to be doing this in two stages, pre-training and instruction tuning or fine-tuning. Here are the data sets for pre-training. So here are all the different data sets they use. CC3M, CC12M. I think CC12M is the same one that they use here in the Stable Diffusion paper as well. Yeah, so Stable Diffusion on CC12M. You see that? So that's CC12M, quite popular. But look at this, 2 billion text image pairs. And then they have captioned images, synthetic. This is the VCAP where they augment those captions. That's 300 million image text pairs of that. Interleaved image text, which is 600 million documents. And then text only, around 2 trillion tokens of text. And there's an interesting kind of comparison that they do here, where captioning data tends to contain relatively short text with high relevance to the image. So captioning data is basically an image with a little caption. Interleaved data has substantially longer and more diverse text with less relevance on average to the surrounding image. So interleaved data is basically like an article from like a news page, right? So like an article from a news page has like 3 pictures in it, and then it has like a bunch of paragraphs of text. And the pictures are only loosely related to the paragraphs of text. Compared to a captioned data set is a image that has exact caption associated with it. So it's slightly different types of data, and they have a mix here, right? I think it's like a 50-50 mix of those two types of data, which is, they say, quite important that you want to have both of these types of things in here. Interleaved data is instrumental for few-shot and text-only performance, while captioning data lifts zero-shot performance. So few shot is basically something like this, right? Where you have a couple different shots. Zero shot would be something more like this, where you basically have one image, one question, and it's like, boom, zero shot on your first try. Do you get it correct or do you not get it correct? All right, let's go back up to here. We were here, image resolution, now with a VL connector lesson, then the pre-training data lesson. Here are their figures. And this is another little bonus point for this paper. So another reason I like this paper is that the figures are very nice, right? So Apple still has the legacy of Steve Jobs, who was like extremely detail-oriented type of person, and he was like very, very interested in kind of like text fonts and stuff like that. So it's kind of cool that all the figures that they have in this paper, they don't look like any of the other figures, right? Usually when you're reading papers, they all use the same plotting frameworks like Matplotlib and all these other ones to make their charts. So all the charts generally look the same because they're just using LaTeX and Matplotlib. They're using the same fonts. But this being an Apple paper, right, they have their own special secret fonts that they use for this. So it is a little visually refreshing to read a paper where the like plots are using different fonts and different kind of formats. But here you see the difference of the pre-training mixture. So caption and interleaved mixing. So 100% captioned, 0% interleaved, which is your kind of like blog article type thing, and then 0 to 100. So you see how the blue and the purple are usually a little bit lower than the mix, right? So you see how here, especially on the 4-shot and the 8-shot, using more of a 50-50 mix of this captioning data and the interleaved kind of blog article type data, is you want the 50-50 mix, right? So these middle bars are taller than these side ones. And similar kind of thing here. Caption plus text, interleave plus text. So here's whether or not you add this text-only data right here, so text only. They mentioned that the reason you want this text-only data is because of you have this LLM in here. So if you don't have text-only data, sometimes the LLM will just start to like maybe ignore the text a little bit and focus a lot on the vision. So during your pre-training and fine-tuning, you want to slip in a little bit of data in there that's only text-to-text so that it continues to put a little bit more attention on the text tokens right here as well, right? So you just don't want it to forget how to read text, because sometimes that can happen with these vision language models. So here they show that caption plus text and interleave plus text, which is these orange and red bars, are generally better, even though like it's a little bit weird here, right? Because why is 4-shot different than 8-shot different than text? Like, I don't know, right? These aren't even that different either. The text makes you think one thing and the figures make you think another thing. Maybe that's not necessarily a good part of this. Text-only data helps with few-shot and text-only performance. Data lesson 3, careful mixture of image and text data can yield optimal multimodal performance and retain strong text performance. So the mix is the best. And then synthetic data helps with few-shot learning. Synthetic caption data, this VCAP data set, which they call captioned images synthetic, which is actually not that much data. It's just 300 million image text pairs compared to 2 billion image text pairs for this captioned images. So relatively small percent of synthetic data, but they do say relatively small, being only 7% compared to all caption data, still gives a non-trivial boost of 2% and 4%. So synthetic captions give you a bigger boost, 4%, compared to, for example, the image encoders. So here, the relative image encoders, right? So going from 224 to 336 image resolution, 3% boost. Going from a VITL to a VITH, 1% boost, 1% boost. So the capacity of the image encoder is less important than using synthetic captioning data, which is pretty cool, right? That's the exact type of like hard, concrete number that most papers don't give you, right? Most papers will probably say, hey, synthetic captioning data is important, but they won't give you that exact percent so that you can compare it to some of the other design choices. think differently equals different visuals. Yeah, basically. But they're cool. Like, I kind of like this font. Some of it is a little weird. Like, for example, here, I wish this 61 would have been 61.0. You know, like, it's a little jarring to not have that be 0.0. And then these horizontal lines, I agree with you. They kind of look a little gross. But, you know, there's probably some Apple like font design wizard who would disagree with me on that and would just tell me I have terrible taste in figures. All right, so final model and training recipe. So all those results, all those experiments that they did, here's the final results. The image encoder is going to be a VITH with 378 by 378 pixel resolution, pre-trained with a clip objective on this DFN5B dataset, which you can access here on their Hugging Face. This is it. DFN5B clip VITH 14 at a 378 resolution. This is probably the strongest clip image encoder, but vision language connector, number of visual tokens is of highest importance. We use a visual connector with 144 tokens using this C abstractor, but they say that it's not really quite important, so I feel like a linear projector is probably the simpler than this C abstractor. And data is going to be a 45% mix of image text document, this interleaved kind of like articles, 45% image text pair documents, which is the captioned, and then 10% text only. Both the LLM and visual encoders are pre-trained, which is pretty standard. And here is the tricky part here. All models are pre-trained entirely unfrozen. So most of these other VLM papers, they freeze them. Right? So they don't train these from scratch. They get them from Hugging Face and then they freeze them. But Apple trained theirs from scratch and also doesn't freeze them. So when they're pre-training the whole VLM, they're actually pushing gradients into the image encoders. Right? So all models are pre-trained entirely unfrozen, which is kind of interesting. Usually people will freeze them, but here they're actually letting the gradients go all the way down into these image encoders, which I thought is new and kind of interesting. Let's see, where are we at? We're here. With a batch size of 512, all models are trained using the AXLearn framework. All right, and here we have a little GitHub link to the AXLearn. Let's actually go to that. What is AXLearn? So AXLearn comes out of Apple's GitHub. All right, cool. Let's go. AXLearn is a Apache 2. All right, Apache 2 is pretty permissive. It's kind of like an MIT, but written by a lawyer. And what is AXLearn? Blah, 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 blah. Boom, here you go. Library built on top of JAX and XLA to support the development of large-scale deep learning models. All right, so Apple is using JAX. There it is, guys. Apple could have done what Meta did and use PyTorch, or it could have done what OpenAI did and use OpenAI uses PyTorch and trains on NVIDIA. Meta uses PyTorch and trains on NVIDIA. Google uses JAX and trains on TPUs. Apple uses JAX and trains on, we don't know. But according to the pattern I just gave you, they might even be training on TPUs, which is weird, right? Like, imagine Apple using their own JAX variant built on top of, or training on TPUs. Like, that seems really weird, right? Is that maybe why they didn't mention it at all in their paper? Is because they're training on TPUs? I don't know. They do. So, for example, here on their Hugging Face, the model has been converted to PyTorch from the original JAX. So it's not entirely clear, right? It seems like they're using something that is like JAX, but then they're also giving their models in PyTorch, and then they don't mention what they train on. So I'm even more confused. Maybe, yeah. I don't know what they trained on, but I think the reason they don't mention it, like I said, is I think it looks bad for them, right? Whether they trained on NVIDIA GPUs or whether they trained on Google's TPUs, that's not a good look, right? So I think they're basically never going to mention that until they have their own chips, and then they're going to say, we trained with like Apple Torch, or they're going to come up with something better than AXLearn, because even the fact that they have to mention that this library is built on top of JAX, I'm sure the people at the top of Apple are not happy about that, right? They'd love to have their own framework and their own chips, right? Apple is all about vertical integration. They want there's no way they're going to continue to train using someone else's framework and someone else's chips. They're going to want to have their own vertical stack. So I think they're working towards that, but they're not quite there. Model scaling. All right, so we perform a grid search of learning rate at a small scale. Optimal peak learning rate n is based on this equation, so they're going to choose the learning rate based on the model size. Interesting little note here, the validation loss wasn't strongly correlated with downstream task performance. Kind of cool, guys. Don't look at your validation loss. That used to be the way to determine which of your models was performing best, but you don't want to be doing that apparently. And they do provide their hyperparameter sweeps over here. So this is a pretty cool visualization. This is a grid search over peak learning rate. So whenever someone says a hyperparameter sweep, what they're saying is that you're going to have to put in a value for your peak learning rate and weight decay. The weight decay, you can kind of think of it as the weights of your model, you let them decay over the course of training so that if an individual little parameter is important, it'll continue to basically receive a gradient that will make it bigger, right? So if a little random neuron happens to get lucky and a gradient makes it a very high value so that it activates very strongly, if you don't have weight decay, that little neuron is going to stay high the entire time. So weight decay kind of like always just like kills your neurons slowly so that the neurons that actually do consistently perform things continuously get gradients which kind of like continue to make them bigger and more refreshed. So it's kind of like a way, it's kind of like a regularization technique to make sure that all the neurons in your network are actually doing something relevant. But the problem with weight decay is that you have to pick a value for that weight decay. Like how much are you actually decaying your weights? And that's a magic number here, right? So you could pick a value of 2.2 e to the negative 3, or you could pick a value of 2.2 e to the negative 5. And learning rate, right, is also arbitrary, where you're kind of just picking some number which represents basically the step size that you're going to take when you move and perform this gradient descent and move around in this loss landscape to some kind of local, or hopefully global minimum, right? And you don't know what the value for learning rate or weight decay should be. So what you do is you sweep over that parameter space, right? So here they're going to be sweeping and they're going to say, okay, let's try a weight decay of 1e negative 3 and let's try a weight decay of or a learning rate of 1e negative 5. And if we try that, we get this. So here, the things that are white are going to be basically high scores, and the things that are this black are going to be low scores. Or I think black means they didn't even try. Black cells correspond to settings we did not run. So they basically sweep, or they train a model at this one. They train model here, they train a model here, they train a model here. And then this is the sweep, right? So this is all the different permutations of these two hyperparameters that they tried. And what they're trying to show you here is that if you say this one worked well at 9 million, they're trying to say, okay, well, that should also work for 85 million. That should also work for 302 million. That should also work for 1.2 billion, right? Because performing this sweep out of 1.2 billion parameters is way more expensive, right? Every single one of these dots here, this is a way more expensive experiment than here, right? This is a 9 million parameter model. This is tiny. So you could perform basically a huge grid search here where you're sweeping over all the possible permutations, but your grid searches here is a lot more expensive. So you want to make most of you want to run your experiments at low model parameter size, and then start increasing the model parameter size, and then see if it basically leads that. Because what's going to happen is that when you're actually going to train the 30 billion parameter model, you're not going to sweep, right? You're only going to train one 30 billion parameter model. So you're going to have to pick a value for the weight decay. You're going to have to pick a value for the learning rate. You're going to have to pick a value for the momentum. There's going to be like maybe not hundreds, but tens of these little hyperparameters. So you're going to have to choose the value for those hyperparameters based on these lower parameter experiments. And that's what they're showing you here. This doesn't necessarily inspire a ton of confidence to me, because like it seems like there's not necessarily a pattern here. Like it kind of seems like this area is kind of good and this area is kind of bad, but like I don't know, it could be the case that if you did this little corner down here, it would be white, versus here it's red, right? So that's kind of what I mean, that we don't 100% know for sure that doing these experiments at low resolution or at low model parameter size necessarily means that that conclusion is going to hold at a higher model parameter size, right? We're just kind of assuming that because there were some papers that said, oh, that's totally fine to do it, but I feel like those are kind of hand-wavy arguments, and I feel like 10 years from now, when we have the compute to actually perform these experiments, it might be the case that even though here it's a bad permutation of hyperparameters, here it's actually a good one. So just a little grain of salt there for them. Let's go back here. All right, mixture of expert models. I think Apple buys H100s. Is that confirmed? Person with a Chinese name I can't mention. Are you an Apple insider? Emily's mentioning mu transformer method, which I assume is some theoretical kind of way of hand waving that hyperparameter transfer is totally fine. Okay, let's talk about mixture of experts. Mixture of experts scale the total number of model parameters while keeping the activated parameters constant. What it means is that really you're making your model bigger, but the total amount of model parameters that you use during one inference actually stays the same because you're not going to be using all of these experts. Adding more experts in the FFN layers of the language model. So I have a little picture here. Here you have a language model. It's kind of cropped, but you see that there's an attention mechanism, then you have a layer norm, and then you have this mixture of experts. What a mixture of experts does is you see how there's multiple feed-forward networks here, or MLPs. And then you're going to have this little router. And in a mixture of expert, you're only going to use a subset of these, right? So in their paper, they say top 2 gating, which means that even though you have 64 experts, you're only using 2 of them. So you're basically, this little router is going to pick the 2 that are the most relevant, and then it's only going to use those 2. So this is another visualization that I show all the time. This is a transformer, Nano GPT. Here you have the input. Here you have, for example, the attention. So here's the multi-head attention right here. And here you can see that this is the multi-head refers to, you see how there's 3 different sets of K, Q, and V weights, KQV, KQV. Each of these is one head, right? What a mixture of experts does, right? A mixture of experts, you have the same multi-head attention, but then you have this layer norm, and then you have this right here, right? So you go down here, here's the attention residual, blah, blah, blah. Here's your layer norm. And then once you go out of your layer norm, you see how there's just one MLP here, right? There's just one set of MLP weights and one set of biases here, right? There's just one. What a mixture of expert does is you basically now have a bunch of them. So imagine this here, but there's a bunch of them in parallel. So there's going to be whatever, 64 of these, right? Which is this feed forward block here. Feed forward, FFN, and MLP, in this case, they mean the same thing. It just means feed forward network or multi-layer perceptron. It's just 2 words that mean the same thing. And what a router does is the router will sit right here, and the router will basically choose which of the 64 heads or which of the 64 experts to route it through. And by doing that, each of these experts can kind of focus on slightly different things. So you end up with experts that are experts at specific types of tokens or maybe specific types of information. It's not entirely clear, right? We've read some of the MOE papers and they've done studies on these, and it's not like the experts are semantically understandable. It's not like one expert is the math expert and one expert is the French expert and one expert is the English expert. The experts are like working in each different token. So like it's almost like it's very difficult to understand as a human. We don't really exactly know what the fuck each of these experts is an expert in, but it works better, right? So that's what a multi-layer, a mixture of expert is. It's basically just more FFN layers. And here they're going to be using top 2 gating, which means you're only picking the top 2. Load balancing. Here they're talking about usually when you train these mixture of experts, one of the issues that you run into is that you have to make sure that when you're training this, you encourage this router to distribute the tokens equally, right? If you don't have these load balancing, what ends up happening is that one of these experts kind of becomes dominant, and then once it becomes dominant, all the other experts kind of atrophy, and then the router just ends up using the same expert every single fucking time. So what you end up doing is you have these special regularization losses that kind of load balance to make sure that the router kind of equally picks all the experts. The image encoder and the vision language connector are kept the same, so there's no mixture of expert there. Okay. How's it choose the expert? There's different ways of choosing the expert. Usually what you're doing is here, mixture of experts, sparse versus soft. There's, yeah, this figure here. So this figure comes from this paper. Here you go. Learn to assign. Okay, I think, where is it? There's literally a definition here of this. Each expert will process P slots, and each slot has a corresponding D dimension of vector parameters. In particular, the input slots are the result of a convex combination of all the input tokens. The D, which is what we call the dispatch weights, is simply the result of applying a softmax over the columns of X. The corresponding expert function is applied on each slot. Finally, the output tokens are computed as the convex combination of all the output slots. So this is soft, where you're basically combining all the experts together. But what they're doing here is hard assignment. So hard assignment just picks 2 specific experts out of the 32. But this here, these dispatch weights, those are the weights that are inside this little router. So this router is kind of like a little mini neural network that is looking at what's coming out of here and then choosing the which expert to put it in. And even there's 2 different ways of doing that. There's like expert choice, where the expert kind of is the one choosing which tokens it gets, and then there's kind of token choice, where the tokens themselves are determining which expert to route to. There's a lot of different types of routers and ways of assigning which expert the tokens go to, but I don't know. Hopefully that works. We can also use BERT. Okay, I don't know what you guys are talking about. Multimodal pre-training results. All right, so here's your results. Again, these results are not like, yes, they're the best. So here are the visual question answering. These are all different VQA benchmarks, captioning benchmarks. So obviously MM1 3B, MM1 7B, and then MM1 30B, the 3 different sizes, outperform all of these ones. So here's your state of the art, right? State of the art, state of the art, state of the art. But it's state of the art compared to Flamingo 3B, compared to Flamingo 9B, compared to Flamingo 80B. So these are old, right? Like these Flamingo models, these emus, like these are not the strongest models. Like notice how there's a clear lack of Claude 3 Opus here. There's a clear lack of GPT-4 Vision here, right? If they would have put GPT-4 Vision on here, they wouldn't be state of the art. So they pick specific things to compare against here to claim state of the art, but they're not comparing to all of them, right? They're kind of like picking the things to compare to. And the reasoning that they say is that these are the open source ones. So they're saying, okay, compared to the other open source ones, we beat them. But it's like, dog, of course you beat them. You're training this fucking giant model from scratch because you're Apple and you can train this from scratch. Like the people who train Emu2 and Flamingo and like these guys are like, they're just gluing shit together from like other models. Like they're just doing this type of shit, right? So I don't know. They're kind of like beating other people that don't really have the same resources and didn't perform the type of sweeps that these guys perform, right? Because Apple's performing much larger sweeps because they have the compute to perform these larger hyperparameter sweeps. So, of course, they're going to be better. All right, supervised fine-tuning. So this is the second part. So we were looking at pre-training, right? Pre-training, you're training a lot longer on a bigger data set, but now you want to fine-tune it, which is training for just a little bit more on a little bit of a smaller data set, but that smaller data set is going to be more specific, right? So the pre-training is done on these kind of generic caption data sets and kind of blog posts where you have a couple images with some text, but now you want it to train it on specifically the task, these kind of like these VQA type tasks, right? So the fine tuning is done on smaller VQA data sets. And the interesting thing that they do here is that the data sets that they use for fine tuning are generated by GPT-4 and GPT-4 Vision. So Lava is a large language visual something. This is one of the more popular series of vision language models. We've actually read a couple of these papers on streams. If you're interested in the Lava series, this is I support all their work. Very awesome stuff. They release all their code, and it's basically was the state of the art vision language model for a while. At least I used it for all my projects. But Lava trained on these synthetic data sets that are generated by GPT-4 Vision. So in a way, right, if you're fine-tuning your vision language model on GPT-4V synthetic data sets, you could rephrase that as saying MM1 is distilling from GPT-4 Vision, right? If you're fine-tuning on GPT-4 Vision, what you're saying is you're instructing your model to say, hey, here's the image that we gave GPT-4 Vision, and then here's what GPT-4 Vision responded with. You need to respond with those same text tokens. Okay, here's another image that we fed into GPT-4 Vision, and here's what GPT-4 Vision said. You need to respond with these text tokens. So effectively, you're distilling GPT-4 Vision. So pretty much every single vision language model is distilled in some way from GPT-4 Vision, which is kind of crazy to think about, right? So GPT-4 Vision has its fingers everywhere because everyone is using these augmented synthetic caption data sets. Everyone is fine-tuning on these GPT-4 Vision generated data sets. So it's such a clusterfuck right now. Like people start talking about like copyright and data ownership. Like, what does it mean when Apple is fine-tuning their model on a data set created by a open source company that used GPT-4 Vision, which was trained on data that we don't actually know what the fuck it is? Like, what I'm saying? The chain of ownership is just so weird there that I feel like we're never going to untangle this Gordian knot, right? The Gordian knot of like, where does this data come from? Especially when you start talking about synthetic data sets that are generated by other models, it gets so complicated so quickly, and it's only going to get even more complicated that I feel like it's just completely unreasonable to feel like we're going to have like any kind of hardcore regulation that comes in and says, okay, it's illegal to train on this, and anybody who trains on that, like, it's not going to happen because everyone's going to be mixed together. It's all just one big giant tangle of data dependencies that no one's ever going to untie. We're just going to move into the future. Everybody's going to be training on everybody else's shit, and it's totally fine because we're going to be living in a UBI utopia, so who cares? But, okay. That's what they train on. Here are some other VQA data sets that they fine-tune on, and here's the one that the only data set that they didn't, that isn't publicly available. So here they mention it, just one sentence here. They text-only SFT, so the supervised fine-tuning data set that is text-only is an internal data set. And they say it's similar to ShareGPT, but maybe they cleaned it. I don't exactly know why they wouldn't release this, but that's the only secret data set that they used. And it's going to be very small, right? Because the text-only SFT, the text-only, we know from up here that it's only 10% of the training data, right? 10% text-only data set. So if they use the same data mix that they used for the pre-training and the supervised fine-tuning, that means that this secret proprietary data set is only going to be a very small percent of the fine-tuning. Okay. Let's see. Question from 87. Do you train the router? Yes. This router in a mixture of experts is going to have some parameters, and those parameters are going to receive gradients, and those gradients are going to change the value of these parameters. Japan did it right by Avant-Garde. They said anything used for training AI and anything generated by AI is immune from copyright lawsuits. I agree 100%. I think that Japan has a huge advantage in that, right? They said, I very much agree with what they did. I think that's the correct way to do it. No IP, doesn't fucking matter. Train on whatever you want. But also, that means that anything your model generates, anybody else can train on. So it makes it completely open. It means that everybody can use everyone's thing, which I think is the correct way to do stuff, right? The problem is here's the problem with that avant-garde is that we're already seeing cracks in that, right? So there was a situation, I think a couple weeks ago, where people in Midjourney realized that some of the people working at Stable Diffusion were scraping their service. So people at Stable Diffusion were basically they just had a bot that just sits there and just types random shit and then gets images from Midjourney, and then they can use that as a data set, right? And then Midjourney banned those people who were working at Stability AI from Midjourney, right? So they said, hey, we don't want you using our model as a source of data, so we're going to ban you, right? But is that illegal? Can those employees of Stability AI, can they sue Midjourney in a Japanese court and say, hey, Midjourney is preventing us access to their model over grounds that we're using it for training data, and that's illegal, and some kind of like discrimination argument, something like that, where it's like you are there's protections like that for discrimination, where it's like you can't not hire someone because they have a disability, right? There's like a law that if someone chooses not to hire you because you don't have a disability, or because you have a disability, you can sue them for that. So I wonder if there's going to be similar laws where someone's going to try to basically sue one of these companies or ban people so that they don't scrape their AIs. And then at some point that's going to go to a court of law, and they're going to say, okay, no, you can't ban people that are scraping your AI for training data. You have to let them scrape your AIs. So I don't know. There's going to be some weird shit. There's going to be some weird legal situations going on. Yeah. Okay, it seems like you guys are also not entirely sure where it's going to end up. I don't know where it's going to end up, right? Hopefully they choose something that ends up... Because here's the thing. If they can ban you for scraping, then people are just going to become more clever about it, right? Then people are going to create a service that mimics a human. So Stable Diffusion employees will figure out how to basically make their bot only ask for images at a cadence that makes it less suspicious, right? So one of the easiest ways to determine that a bot is scraping your service is that it's pinging 24/7, right? So if it pings every minute for 24 hours for 7 days straight, that's not a human sitting there typing into Midjourney. But if it only pings like between the hours of 9 and 5, and it pings every 10 minutes, and it pings different things, then it's very difficult to know if that's a bot that's scraping or if that's a human that's actually just typing things into Midjourney. So if legislation ends up getting passed that prevents this type of scraping or allows a company to ban someone because they're scraping, people are just going to become more clever about how they scrape, and they're going to scrape in a way that's very difficult to tell whether it's a human or a bot that's scraping. And especially now that we're moving into a world where CAPTCHAs don't really work, and the click here if you're a robot doesn't work, and like all the different ways that kind of automatically try to tell if it's a bot or a human, it's going to be an absolute mess, right? And then if somehow they figure out this kind of bot detection that is super advanced, then maybe Stable Diffusion will pay you, right? They'll pay you, some random guy, to sit there and type random things into Midjourney and then put it in a zip file and send it to them because you're a human and they can't say that I don't know. It's going to get really weird really fast. Yeah, scrape by randomizing the polling time and IP. Everybody's stealing everybody's data, and I'm totally okay with that. I think that's actually good. All right, let's get back to this paper, though. Okay, so positional embeddings. Maybe we can talk about positional embeddings for a second. There's nothing really fancy going on. They do this positional embedding interpolation, which we saw in the Stability Diffusion paper as well, where basically to support different image sizes, you basically have to make sure that your positional embeddings don't get messed up. We use a combination of extended and interpolated position grids, which are subsequently frequency embedded, so that our position embeddings, which are basically just a bunch of sinusoids that you stack on top of each other in clever ways, in order to tell the language model where specific image tokens come from relative to the image, right? Is it the middle of the image? Is it the top corner of the image? Is it the bottom corner of the image, right? That's what the position embeddings are telling. But if you want to support different sizes of images, which in this case Apple does, right? Because you want to be able to feed different resolutions, a wide angle, an image that you took like this versus an image that's vertical. So they do the same type of positional embedding fuckery. Here's a little trick. For a high-resolution input image, we first downsample the input image as a high-level representation and then also resize the input image and divide the resized image into 4 sub-images. So I thought this was kind of weird. So if you try to give it a very, very big image, because that very, very big image will result in a huge amount of compute whenever you're trying to feed it into this vision encoder, and then the amount of tokens will be big, they'd rather feed a very small resolution version of it and then cut the image into 4 chunks and then feed each of those 4 chunks individually, right? So kind of like a weird little hack that they do there. Gemini Nano 2, what is this? Comparison of state-of-the-art benchmarks for models on MMLM benchmarks. Yeah, so here, this is the... So remember how I said up here, they claim state-of-the-art by comparing to these other ones here that are not as strong. This table here, this is more the real comparison. So you see here, they're actually comparing to Lava Phi, Gemini Nano, Lava Next 7B, Qwen VL Chats. These are more impressive, right? So now they're really not state-of-the-art, right? Compared to, for example, GPT-4V. Ooh, actually kind of. On VQA, GPT-4V gets a score of 78. Gemini Ultra gets a score of 82. MM1 30B Chat gets a score of 73. So it's not quite state-of-the-art, guys, but it's pretty good. Here we have some of the Cog VLM 30B, 68, 83, 83, 77, 78. So it's about on par. It seems like a little bit worse than GPT-4V and Gemini Ultra, a little bit better than the open source ones, but not quite GPT-4V, which is, of course, strange because, of course, they're fine-tuning on GPT-4V. So in a way, they're distilling GPT-4V into this model just a little bit. Okay. Our MOE models achieves uniformly better performance than the dense counterparts on almost every benchmark. This shows great potential of MOE for further scaling, which is left as future work. I kind of feel like MOE is cheating, to be honest. I feel like it's just a way of increasing the parameter count without increasing the parameter count, but it glosses over the complexity of like loading things in and out of memory, which I think is just an additional bullshit overhead that you don't have to deal with for dense counterpart, which is a model that doesn't have MOE. So I don't know. MOE is, I feel like I said, I think it's a trick that people came up with for these server clusters that only makes sense in that server cluster when you have these like batches of data that you're feeding in from a bunch of users at the same time. But people have realized that it's kind of a way of cheating these benchmarks because a 3B MOE with 64 experts is still considered 3B, even though the fact that 64 experts means that the total number of parameters in the 3B MOE is more like 10B. It's just that you're only using 3B of them. So I don't know. I feel like the MOEs are a little bit cheating, but whatever. Everybody cheats the same way, I guess. Impact of image resolution. So small image size, 224. Big image size, 1792. Average evaluation metric. So this is like a kind of like a ensemble of a bunch of different evaluation scores. You see kind of the obvious trend here where the bigger the image, the better the score. And here pre-training steps. So roughly an idea of how much data it's seen, how many tokens it's been trained on, and then average evaluation metric. So increasing on both of these, which is what you want to see, right? There's a little bit of a dip here, but that's probably just some nuance of the architecture. And this means that next year, once we can finally start training things here, right? Maybe next year we can do 4K image resolution. It'll be up here. And next year we'll have 2,000 pre-training steps. It'll be up here. So actually, I guess it'll be 100 because the average evaluation metric can't be more than 100. But it's going to get stronger when we increase that scale, which is really the only important thing. Model consistently improves as it has seen more pre-training data. Different VL connectors have negligible impact on final results, which I think is also indicative of just model architectures in general, right? I think that 10 years from now, no one's going to give a shit what the model architecture is. It's largely just going to be like, what was your data? And then what did you train, or how long did you train it for? And what is the size of the model? And that's pretty much it, guys. Let's see if there's a couple other things that I wanted to show here. This is talking about the data set. They do apply the image filtering and image deduplication, so that's something that we see time and time again. Bringing up the stability paper again, they also do this. So they also do deduplication as well. We carefully scan our training data set for duplicated examples and remove them. So cleaning and data set deduplication, kind of obvious data filtering that everybody's doing. Here's how they create the blog articles that I was talking about. So they get these HTML files. We extract the text body layer and all the image tags. We remove the documents that have no images and more than 30 images. So this is how you get kind of the interleaved, where you have a higher ratio of text to images. What else? Let's see. Here's the supervised fine-tuning data set. 1.45 million is created by all of these together. Here's your GPT data. These are also GPT datas. So this is distillation of GPT. During SFT, we keep both the image encoder and the LLM unfrozen, as empirically we observe that fine-tuning the whole model achieves better performance. This is something new, right? Because like I said before, pretty much every other vision language model paper that I've read freezes them, right? So usually these encoders are frozen, but here, because they're Apple and they have the budget to do so, they unfreeze them so that they can push gradients into them. Outputs are generated with greedy decoding, which means they're just picking the best possible token at every single time, right? The decoder language model is auto-regressively outputting one token at a time, and they're not doing any kind of temperature sampling or anything fancy like that. They're basically just doing greedy decoding, which is just picking the best possible token at every step, which I think is what you want to do if you're doing this kind of paper where you're kind of performing an experiment, right? You don't want to introduce more randomness in there. All of our multimodal pre-training evaluations are implemented in an internal fork of Eleuther AI's LM evaluation harness. So there you go. If for those of you that are interested, you can use, even Apple is using Eleuther AI's eval framework. So they're using Google's framework for the model architecture, which is JAX, which is actually where you're going to have your training loop and how you're actually going to define your model and all of that. And then they're using Eleuther AI's evaluation framework, which is weird, right? I feel like they should have just written their own versions of both of those, but it's a lot of work and they'd rather not do that. Let's see what else. Average pool C abstract. This is the vision language connector, kind of showing you that it's a wash. There doesn't seem to be one that's better than the others. They're better at different times, which means that none of them is necessarily the best. Here's different mixes of data. Unfrozen encoder, frozen encoder. Yeah, so it does seem like the bigger you make the image resolution and the more tokens for each image, if you have the budget to unfreeze the image encoder and push gradients into it, you could do that. At lower resolution, a frozen image encoder results in better performance. At higher resolution, it's beneficial to unfreeze. This is some of the more fancy shit they're doing again, where they're sizing these images differently. So because every image is going to be turned into a sequence of tokens when it's fed into the language model, right? Where is it? Right here. So if you have 5 images, right, you're going to have 5 times as many tokens. And if you have 5 4K images, that might even be your entire context length, right? So depending on the number of images and depending on the resolution of images, they're going to basically downsample some of those images. So if you have some kind of OCR task, like this one, for example, where you have very tiny text in an image, don't give it 10 of these images at the same time, because if you give it 10 images, it's going to downsample those images, and if it downsamples those images, it's not going to be able to read very tiny text in a very downsampled image. So, but if you're giving it like this type of image, this answering this question from this type of image doesn't really matter if this image downsampled or not. So just like a little bit of tricky nuance there but I think that'll eventually go away, right? I think as the context length will get bigger, we won't need to do this kind of like image resizing and depending on the number of images, just because the context length is limited. And I think that's pretty much it, guys. Oh, I also found this. They use weights and biases. So they're using weights and biases for experiment tracking. They're using Eleuther AI for evaluation. They're using JAX for the framework. And they're using either TPUs or NVIDIA GPUs for the training. And they're using GPT-4 data sets for the fine-tuning. So, you know, at least they trained their own clip. So, you know, they trained their own clip. At least they didn't use the clip that OpenAI trained, and they didn't use the segment anything or the dyno that Meta trained. But I guess they're less afraid. They couldn't do all of it, right? So as much vertically integrated as they want to be, they couldn't quite do it all. And that's pretty much it, guys. That's MM1. How do they handle non-square images? By resizing or by cropping, or do they use padding? I'm not 100% sure on that, to be honest. It's probably somewhere in the appendix section here. Pre-training, SFT, image encoder, representations, blah, 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 blah. We demonstrate the effectiveness. I don't exactly know. It might be somewhere. Let me see. If I search for crop. Here we go. The word crops. Crop. It's somewhere on this page. Image crops. Okay, so they do crop it. If your image is too big, they're going to crop it into these 4 images. But what about resize? Here you go. We first downsample the image to 672 by 672. So if it's not square, what does that mean? Resize the image and divide resized. We support image resolutions. All of these are square. So they only support square images, which means that they probably crop, if I had to guess, Avant-Garde. But if you figure out the answer to that, Avant-Garde, let us know. Actually, here, we can look at their experiment. So in their examples, are any of these not square? This one isn't square. Most of these aren't square, but the questions that they ask don't really matter. It's not like if you crop this into a square, you could still answer this question. So I'd be curious if someone has access to this, give it a problem where like one of the answer to the question is like in the corner, and then see if it could answer it. Actually, here you go. Look at this. This one is not square. It's very long, and it gets it correct, which means that it's not cropping this away. Probably it probably is even more complicated than that. I bet you there's some heuristic hard-coded thing where like if the image is wide enough that it can be cut into 2 square images, it'll do that. Maybe it like kind of does a multi-crop where it does like overlapping crops that are all square. I'm not entirely sure, but there's probably some fuckery. Shinx X. I bet you are an Android user like me. That is correct. I use a Pixel phone. Okay. Okay, Timothy L is saying that the Sphinx X paper is where they talk about the cropping and the square versus vertical versus horizontal. So maybe check that out if you want to know the details. All right, let me sip this water. Let me summarize what we got. They probably don't use the Python image library, if I had to guess. I feel like Apple has very good computational photography, right? They have like very advanced like image crap just because of their cell phones use so much fancy stuff, right? Like the image you take with an Apple iPhone, like there's like 3 cameras there, and those 3 images are being like cropped in like all kinds of weird ways and like combined in all kinds of weird ways. So they probably have their own internal kind of like image library that's written in an extremely performant, like low-level language. So I bet you they're probably using that, but who knows? Maybe they're using PIL. All right. I'll give you guys a short summary. Let's see. Today, we reviewed MM1, which is Apple's vision language model. Of course, they don't want to call it a vision language model because they want to have their own name for it, kind of like spatial computing and VR. So they're going to call it a multimodal large language model, which I think is a terrible name. This paper is quite good. It's a very good paper. They describe all the different things that they do to train their vision language model. In terms of raw performance, it's competitive, but not state-of-the-art. So let's go to the actual chart here. It's about on par with, for example, Gemini Pro, but not quite as good as GPT-4V or Gemini Ultra. The data set is kind of this giant mishmash of, in pre-training, you're using CC12M. You're using a bunch of interleaved kind of documents, web documents. You have a little bit of text-only data. They use a 50-50 mix between captioned data sets and kind of interleaved data sets. They also have a small 10% amount of this text only. The training is done in 2 stages. So there's a pre-training stage and a fine-tuning stage. I think the fine-tuning and pre-training both use similar mixes. And the fine-tuning actually uses some GPT-4V data, which is kind of interesting. It means that, in a way, this model is actually a distilled GPT-4 vision model. They have a bunch of learnings, so if you don't have time to read the paper, I would recommend just scrolling through and reading these bolded points here, basically kind of like a best practices, such as image resolution has the highest impact, followed by model size and training data composition. So they did a lot of ablations on this part here, the projector, or sometimes also called the connector, which is how you connect an image encoder, which has been pre-trained, to a language model, which is how you create these vision language models. It turns out that the architecture for the connector isn't very important. What really matters is the capacity of your image encoder. They use a contrastive loss to train this image encoder, which usually is popular because contrastive losses give you semantic kind of feature embeddings compared to more nuanced low-level embeddings, which you get from reconstructive losses, such as Dino. But I think they missed out on the opportunity to use ensembles, right? Which we see in a lot of open source models, such as this one here, where you use an ensemble of vision encoders, or such as the Stable Diffusion paper, where they use an ensemble of text encoders. I think that's a very good way to do it, but I think for simplicity reasons, Apple eventually wants to run these on an iPhone, right? You don't want to have to run like an ensemble of image encoders. So I think they just went for the cleaner solution, and they just train their own clip. So now Apple has their own clip and OpenAI has their own clip. I think there's a bunch of other clips too. I think Meta might even have their own clip. I'm not entirely sure about that, but we're seeing people are preferring to train their own encoders just so they don't have to use other people's encoders. But the open source community is going to do that because training encoders is expensive and ain't nobody got time for that. So, but Apple does, and they do have the money to do that. What else? We see the scaling laws are still in full force, so it does seem that more data, more pre-training, so having more data, training for longer, and increasing the image resolution, increasing the context length, like all of the scale dimensions, the bigger you make them, the better the performance is. So we're going to see better versions of these models next year and better versions of the model the year after that. We're not hitting a wall. The only wall that we're hitting is the hardware and the scale, which is the bitter lesson. What else? Oh yeah, the one thing that they don't mention, which was a little bit suspicious, is that they don't mention the hardware that they train on. So we don't know what they trained on. I have a theory. I think that because they use this library built on top of JAX, I feel like maybe they're training on TPUs. I know that sounds crazy, but TPUs are pretty cheap. You know, Google's basically just giving them away at this point. So maybe they train this on TPUs, but I don't know. The other obvious choice is NVIDIA GPUs, but they don't tell you what it is, so I don't know. Suspicious. Other than that, I'm really glad. I think this paper is refreshing. You know, I feel like it would have been very easy for Apple to just be very secretive. It would have been on brand for them to be very secretive. So I'm super happy that we have another big tech company that is choosing to be transparent. You know, it was really only Meta that was being transparent, and now we have Apple that is being transparent. So I'm glad that we've got some wins here for the open source community, and hopefully people can take some of these learned model or some of these pre-trained models, and they can take some of these best practices and lessons that they've come with, and we can apply them to more open source models, and hopefully open source wins. You know, it would really suck if GPT-4 Vision continues to be the state of the art and we just continue to have to lag behind these closed source models. How cool would that be if MM2 next year is better than GPT-5 Vision? That would be so badass. That'd be awesome. But we'll wait to see. All right, guys, thanks for attending. Hope that was a cool and interesting session. You trained a very large, okay. Thanks, Majetti, Timothy, Work, Amelie, Avantgarde, 2ARX, Saskia, Ed, who else? South CX, Khalil, Sakoon, 2ARX, I think I already said your name, Lucas, Majetti, of course. No Free Will. 87GN. Oma Viva. Work. Isaac. Aries. Ed. More Sasika. You guys were popping off. Damn, this chat was Longtran. Isaac. Rachel. And 2ARX again. I guess if I didn't say your name, I'm sorry. Thanks for attending. Hope this was useful. Have a great time. Come join the Discord if you want to talk about this more, or if I said anything wrong, or if there's anything you want to clarify, or if you want to talk about what the state of the art is. But you guys have fun. Have a great weekend, and see you guys later.